For centuries, humanity has gazed at the stars and wondered how to reach them. But the vast emptiness of space stands as a formidable barrier. Our rockets must carry fuel, and even solar sails pushed by sunlight face a problem. As they move outward, the sun's push weakens. In fact, a simple calculation shows that to break free of the sun's gravity directly would require a sail less than 1,000th of a gram per square meter, far lighter than any material we can build. Even ambitious schemes like Breakthrough Starshot, which envisions a giant 100-gigawatt laser to beam a sail, come with enormous engineering challenges. Clearly, exploring beyond our solar system demands new ideas. But what if we could use sunlight in a cleverer way? Instead of trying to race away from the sun immediately, one team of researchers proposes to stay near it and store the sun's energy until we're ready to depart. Dr. David Kipping and colleagues at Columbia University have introduced a concept they call T.A.R.S, the torqued accelerator using radiation from the sun. In TARS, two lightweight sails are joined by a long tether, one side mirror-like and the other dark, and they spin like a giant windmill in space. This setup acts like a flywheel battery. Sunlight slowly adds rotational energy rather than pushing the craft straight outwards. Imagine a pair of rectangular paddles in space, connected end to end. One paddle shines bright like a mirror on its sun-facing side. The other paddle absorbs most light. Because reflected light transfers more momentum than absorbed light, the uneven pressure creates a steady torque. In other words, each time sunlight hits the sails, it doesn't just push, it twists the structure, much like the light-powered spinning you see in a Crookes radiometer toy. Over weeks or months, this subtle, continuous torque spins TARS faster and faster. In effect, the sun is charging the craft's rotational energy store. Once TARS has spun up near its design limit, the climactic moment arrives. The tether between the sails is under enormous tension, right before it would snap. At that point, the system intentionally releases one or both sails and the tiny payload they carry. The result is a high-speed launch. The released sail or probe flies off tangentially to the rotation at a large velocity, on top of the orbital motion it already had. In practical terms, the payload is flung out at escape speed or higher. After release, the freed sails still feel sunlight pressure and keep accelerating, but the big boost has already been given by the spin. This cleverly sidesteps the usual solar sail problem of decelerating as you approach the sun. TARS stays near the sun until the last moment, soaking up maximum sunlight before zooming outwards. What makes TARS different from a conventional solar sail? First, it doesn't hurtle away from the sun while charging up. It orbits in a special sub-Keplerian quasi-path. That means radiation pressure partly counteracts gravity, so TARS can remain close to the sun rather than drifting into dim regions. In contrast to rockets or laser-pushed sails, TARS needs no propellant and no enormous external laser. Its only fuel is the sun itself. In fact, the researchers point out TARS would be a low-cost solution for small probes when building a 100-gigawatt laser is impractical. Rather than firing photons directly at a sail to push it, TARS uses the photons to spin and store energy, and only unleashes that energy in a final kick. The proposed designs use real materials. The sails themselves could be made of ultra-thin carbon materials like carbon nanotubes, CNT sheets, with a coating just a few dozen atoms thick. Graphene would be stronger, over 100 GPa tensile strength, but large area graphene is still hard to make. CNT sheets are lighter at around 1.6 grams per meter density with tensile strengths up to 20 GPa, and they can be manufactured today. With such materials, the entire TARS rig might be on the order of tens of meters across, but weigh only around a kilogram or so. For example, one detailed design was about 63 meters long, 7 meters wide, and only 2.6 microns thick, stowed into a normal launch fairing and then deployed in space. That model needed about 3 years of solar spinning to reach roughly 12.1 kilometers per second, then jettisoning its payload at about 40.4 kilometers per second, enough to break free of the sun. For comparison, 40 kilometers per second is about 0.013% of light speed, far below the relativistic speeds often discussed in interstellar plans. How does this stack up against other concepts? Breakthrough Starshot's goal is to hit 20% the speed of light using a powerful ground laser. Starshot's extreme 0.2 grams per meter sail could reach just 10 kilometers per second in under a week, vastly quicker acceleration than TARS. But Starshot's hardware, gigawatt lasers, massive infrastructure, is hugely complex. TARS is much slower but uses only sunlight. In fact, even exotic TARS variants would fall far short of near-light speed. The Kipping team estimates that even if you boost the system with tricks like charging the sails electrostatically, you might at best get to 0.3% of light speed, about 900 kilometers per second, which would still take on the order of 1,000 years to reach our nearest stellar neighbor, Proxima Centauri. It's an interstellar trip measured in millennia, not decades. TARS also faces practical hurdles. Its acceleration is extremely gentle, so the spin-up phase takes a very long time and the craft must survive that long in a stable spin. The whole system must avoid tumbling or breaking apart prematurely. Its performance is ultimately limited by material strength and thermal constraints near the sun. In one study case, a TARS design massing only 1.6 kilograms could send a smartphone-sized sail into interstellar space within a year's worth of sunlight, but the speeds achieved were still well below those needed for true relativistic travel. In short, TARS can get a small probe out of the solar system without rockets or lasers, but it cannot achieve the breakneck speeds envisioned by laser-driven concepts. So, why does TARS matter today? It matters because it broadens the toolkit of real-world science. It shows that even using only the sun's light and available materials, interstellar flight is not purely science fiction. A TARS-like mission could potentially launch many tiny probes over time at relatively low cost, exploring nearby stars with technology we can already build. It reminds us that imagination in engineering can reveal hidden possibilities. Rather than pushing a sail directly away from the sun, we can charge a sail like a battery and then release that energy when ready. TARS is still a theoretical concept, and it requires further study before it could fly. But even as an idea, it helps guide research and spawns new questions, exactly the kind of advance that keeps space exploration alive in the real world. TARS was detailed by David Kipping and Catherine Lampo, Columbia Univ, in 2025. Their analysis available on Arxiv calculates mission profiles, materials, CNT sheets, and orbits. We also reference news and NASA material on solar sails. All facts above come from these current scientific sources, which are mentioned in description.